Hello, Professor. This is my recording of my project on the SIR model by me, Faraz Kaberi. So let's get straight into it. The SIR model is a set of three different differential equations that kind of talk about how diseases work and how they change over time from by people. So everybody starts off susceptible, everybody gets infected, and then everybody recovers. So how that kind of works. Um, the reason I chose to do this one is because being in computer science, you really want to know these helpful differential equations and equations so that you can put them into use, create programs, which is something I did for this project. Create programs to help these kind of confusing differential equations go by really easily. And something we'll see later is that this one can't be solved, but using analytics and computers, you can solve some aspects of it. So that's kind of why I chose it. And yeah. So the creators of this differential equation are William Ogilvy Kermack. He was a biochemist. He was interested in chemical kinetics, biochemistry, mathematical modeling, and biological process. His work remains essential to understanding the infectious diseases or how infectious diseases spread, particularly during pandemics like COVID-19. And all of those relate back to the SIR model and how it helps model diseases and how we use that model to fight those diseases and predict and map out timelines. The second person is Anderson Gray McKendrick. He was a Scottish physician, epidemiologist, and he pioneered the use of mathematical methods to model the spread of infectious diseases, and that's the SIR model. And he also combined medical practice with mathematical and statistical modeling. Again, the SIR model. He took math and he applied it to medical stuff, which is diseases, and that's that. One thing to note is that the SIR model is not their first version of by Ederson and the other guy. This is actually one of their later versions. They're probably their last one, I'm assuming. Um, they made other versions that were a lot more complicated and accounted for a lot more things, but they were just too hard to analyze at the time. And this way, with this one, it was a little bit simpler to analyze, and it made it a little bit easier to study, made it easier to analyze, as I said, and then also made it still useful. So this one's a little more bare bones, but it's still useful. The SIR model equations, here we are with the three different ones. So that top left one is ds over dt is equal to negative b times s of t times I of t. To the right of that is dr over dt is equal to k times I of t. And then to the bottom of that is di over dt is equal to b times s of t times I of t minus k times I of t. And this is where S of t is the number of susceptible individuals, I of t is the number of infected individuals, R of t is the number of recovered individuals, um, beta or B is a transmission rate, K is the fixed fraction of people that recover from the disease in a day, and T is the unit of time, which is usually days but can be measured in, I don't know, I guess minutes, months, years, whatever. Um, to kind of explain the equations, that top left one is shows and represents how susceptible people shrink over time. And this is because susceptible people get infected through contact with infected people. To the right of that, the K times IFT, that one just kind of represents how the number of recovered individuals increase over time as more susceptible people get infected, and then after that, like as time passes, those infected people get um, recover, so that's increasing. And then that last one is kind of just showing how the number of infected individuals changes over time and how the infected people increase when susceptible people get infected and decrease when infected people get recovered. Um, and it also shows that the number of infected people grow if and only if the number of infections happens faster than the number of recoveries, and shrink if and only if the number of recoveries grow faster than the people getting sick. Um, there is no solution to the set of differential equations, so there's no general closed form solution to the full linear SIR model. However, you can get numerical solutions to compute S of t, I of t, and R of t over time if given parameters and initial conditions. And something cool I did with that is I actually made a program. I gave myself initial parameters and some initial conditions and made a program. So I'm going to show you that. Here's the program. So the parameters I got were b is equal to 0.3, k is equal to 0.1, dt is equal to 0.1, and t. So I wrote down what they mean. B is the infection rate, k is the recovery rate, 0.1 is each timestamp, and then t is the total time, which is 10. This is just a bunch of coding stuff you don't got to worry about. This is the initial conditions. S of 0 is equal to 0.99, I of 0 is equal to 0.01, and then R of 0 is equal to 1, or equal to 0. And this is pretty much saying that the number of susceptible people is at like maximum. Everybody's susceptible in the beginning. And then this I of 0 is saying that one person got infected, and then in the beginning nobody's infected, or nobody recovered, sorry. And then this is using Euler's method to loop the iterations all the way till the end. And this gives us this data set right here. So the number of susceptible people is maximum, except for 1. You would have to times this by however many tens to get your number of people, but everybody's susceptible. One person got infected, and there's 0 recovered. And then as time passes, each timestamp, somebody gets infected, and the number of recovered people go up. So susceptible goes down, infected increases until it peaks, and then it will start to go down again. And then recovered always increases. So if you were to run this table all the way till the end, the number of recovered people will be the max. Another cool thing to note about this is I only ran this for 20 iterations, 2 minutes, 10.1 each timestamp, so 20 iterations. You can run this for 10,000 iterations. I'm assuming the people with the top supercomputers are running this for 10,000, 100,000, millions, tens of millions with those supercomputers. They're running these iterations like a gajillion times. I mean, that's kind of the cool thing about computer science. Like if we did this by hand, this will probably take just these 20 iterations will probably take like 20 pages. But I only had to do it one time in code, and then I just ran it 20 times. So that's kind of really cool about programming and differential equations like this, that you really don't have to do it too many times. And those top computers, they can run it 20 billion times. Like if I ran it 20 billion times, my computer would light on fire. But I don't have to. So that's kind of just something cool that I did. Let's go back to this. So some applications of the SIR model is obviously to understand diseases in populations over time, and the speed of outbreaks and when it'll peak. Again, if I ran that code for longer, we will see when the disease peaks and then it will start to decrease again. Another key thing that scientists use to define the disease, another key way scientists use it is to define the disease's behavior using real-world data. Scientists can determine the basic reproduction number and the average number of people an infected person will infect, and that usually just shows us how dangerous the disease will be. And another thing, you can also use it to test effectiveness of vaccines, quarantine, and social distancing, like during COVID-19. So if you introduce those things, will the number of infected, will the peak go down, kind of. So there's a lot of different applications to this using the SIR model. These are just a couple that I put down here. Here's a graph to kind of represent the SIR model and how everything kind of works. So pretty much how you derive a graph like this is you just run the data, run that program that I made. You run it like a bajillion times, like 100 data sets here. I don't know how much there are exactly, but something like that, and then you just plot the points. So as you can see, blue is susceptible, red is recovered, and green is infected. So in the beginning, everybody's susceptible, and as time passes, everybody gets infected. So now nobody's susceptible because when you recover, you're immune to the disease. In the beginning, nobody's infected and nobody has recovered. So you can see that's why that's at 0. But as time passes, one person gets affected, and then people start to get infected, and then that goes up until it peaks, and then everybody it peaks out as infected, and then they start going down again. And you can see as red increases. Red increases until it plateaus at the top, where everybody has increased, or everybody has recovered. Cool thing to note about a graph like this is everything is proportional to everything else. So the number of susceptible people decreases as the number of infected people go up. So that's like opposites. And the number of recovered people only ever increases as the number of infected people happen because you can't recover if nobody's infected. So that's just kind of a cool thing about that. Everything is proportional to everything else. Finally, conclusions. My final thoughts on the SIR model. The SIR model is really cool. Obviously, it's something one of the more like, excuse my language, badass differential equations because it actually is one of those ones that actually is helpful. It used in the real world, and in the real world, I mean the big universe world, like everybody, because the COVID-19 hit everybody, and SIR model was used to represent that. So you can't get bigger than that. So I really thought that was cool, and it's one of those ones that help people. So like that's a little bit why it also hit home for me. Like sure, differential equations that represent animal hunting is cool and all, but the SIR model was really one that we use to help other humans, so which is why I really like why it really attracted me and why I thought it was really cool. Some questions I have for it though are this is like a really complex version of what I'm gonna say, but um, how does the SIR model um, account for other diseases that are kind of transmission in different ways? So, example I put here was a malaria, because I know that malaria, some people are immune to it genetically. So you could just be born immune to malaria, and some people are not. So how would the SIR model kind of account for something where people are already immune? Another question here is the how does the SIR model account for reinfection, and if not, or does it account for reinfection, and if not, what changes can be made to introduce reinfection to the model? That one's kind of straightforward. Um, but yeah, uh, that was my presentation. Thank you for listening, and thank you for watching.